Hey everybody, today we are going to be working on the water universe. Today we are going to be working on the University of Waterloo's Canadian Computing Competition Junior 5 problem from the year 2020. So this problem is actually a little bit tough if you don't know how to do it. In fact, if you don't know how to do it, it's virtually impossible, right? So, well, I guess that's the same for almost everything, but for the most part, like this one is not anything you can just kind of figure out on the fly. All right, so basically what you have is they give you this grid, and the grid can be any rectangular dimensions. That could be anywhere from 1 to 1,000 by 1 to 1,000. It doesn't have to be a square. So as I said, it can be rectangular. All right, and basically they're going to give you a set of numbers like this, okay, and in these coordinates. And the coordinates are important. All right, now we are going to save this into a two-dimensional array, but the values in them, the coordinates are important. So normally this would be 0, 0 in a 2D array, but in this one, the problem specifies that this should be 1, 1, right? Similarly, this should be 2, 3 in a two-dimensional array, but it should be 3, 4, right? So we're not including any zeros. So basically, it's like similar to a Cartesian coordinate grid. Now the problem says that we are going to start here in this top left corner at the number 3 in spot 1, 1. And then what it says is that we can go, our target is to try and go here, okay, into the bottom right corner. But in each step, we can only go to places whose XY product is equal to the number in the current cell. All right, that's a little bit kind of confusing, but essentially it means this. Because there's a 3 here, we can only go to other cells whose product of their XY values is 3. So this means that we can only go to 1, 3, so here, or 3, 1 from here. Okay, now once we get to 3, 1, right, then we have a 6. Now, we can either go to 1, 6 or 6, 1, but those aren't on the grid because they're outside the dimensions. So then we can go to either 2, 3 or 3, 2, right? So there's 3, 2, 3, 2 right here, or 2, 3, right? From 1, 3, we could go to either 1, 8 or 8, 1, which don't exist, or 2, 4 and 4, 2. 4, 2 doesn't exist, but we could go to 2, 4. Now, both the 6 and the 8 will eventually lead us to either 2, 3 or 2, 4, which has a 12. And that is our target number, because what we want to be able to do is we can use this 12 and say that's 3 times 4, and we can get to this target, and that's the final destination that we're looking for. All right, so well, how do you do this? Okay, well, what we do is we set up something called the breadth first search algorithm. And if you don't know about this, then I encourage you to watch my other video, which I will link in the description. Okay, so what we're going to do here is we are going to say, we're going to start in this 3, 1. Right, now from 3, 1, there are some places we can go. Right, so we can go and we can say, well, first of all, we ask, is this a solution? At the first, in spot 1, 1, is there a 12 there? If there is, we can go directly to the end and we just found the solution. But there's not. So what we do is we actually say, okay, well, where can we go from there? Right, well, we can go to 1, 3. And so what we do is we actually take this 8 and we place it, I'm going to have to make that a little bit larger there, place it into our possible pathways array, right? And then what we do is we add it to one of the possible places we can go, or one of their possible paths. Similarly, we also add this 6 here, right? And then we say, man, that's ugly. Okay, so we say the possible pathways is 8 and 6, right? So what we do from there is we say, okay, well, we are going to search along the breadth of the tree. So we are going to search across the horizontal section of the tree, not a vertical section. If you were looking vertical, it would be a depth first search. So we're going to move across to the 8. And we're going to say, okay, well, is the spot in 1, 3 the solution, the target that we're looking for? Is that the 12? Well, no, it's not. Okay, so then what we do is we say, okay, well, if the 8 is not, where could we go from there? And we could go from because it's an 8, we can go to 1 8 or 8 1, which doesn't exist. We can go to 2 4, which does exist. So we say we put that 12 there in 2 4. All right, and then we can say, oh, well, we found it, right? Or we would add this to the tree. Okay, and in this case, because we're doing breadth first search, what we're doing is when we add this, we can say, oh, look, that's the target that we're looking for. So from there, we can get to the 12, which is the target, and we can find the solution. Now, if we ever finish exploring, right, so we get all the way to the end of the exploration, and we looked at all the possible pathways that we could be led to, and we never find the target that we're looking for, that means that this path is not possible. Right, and that's basically what the question is asking, is to say if it's possible to even get there or not. It doesn't actually say the fewest steps, but I think our algorithm will actually find the fewest steps. Okay, so anyways, let's take a look at that and start coding. So in the code, we are going to start by just looking at the first version of the solution I made, which will get you through most of this problem. However, one of the things you have to consider is that, especially in most of the competition problems, they have a time limit. And in the Waterloo one, they have a 2-second processing time limit. Now, because they specified that the dimensions at a maximum would be 1,000 by 1,000, you know that that's actually what they're going to do. They're going to give you a million item array to try and traverse, right? Which makes the depth first search impossible. So the first part of my code will just show you how I did this originally, and then I'll show you some efficiencies that you can use to be able to solve and be able to make your algorithm work under the time limit that's is constrained to. Okay. So the first thing we're going to have to do is take in the data entry. Okay, so we are going to say int rows and then columns. So we need to know how many rows and columns. In the problem, they describe them as m and n, but I don't really like that. Okay, so cn rows, cn columns. All right, next thing is we're going to have to actually create the array that we are going to be storing the data values in. So now, one of the things is that when you create this, you can't just say rows times rows by columns, because we're not including the 0 value. We have to start in position 1, 1. So when we create this, we have to say rows plus 1, columns plus 1. Okay, then what we're going to do is we're going to specify the size, which is just rows times columns, right? Now, in your code, you can just say rows times column all the time, but you're going to have to actually do this fairly frequently, and it will actually create more processing because it'll have to recalculate this over and over. So this is, I define this for efficiency. Okay, to save operations, right? So I don't have to calculate it again. And then basically what we're going to do is we are going to read in the data. All right, so in order to read in the data, we're going to say int x is equal to 1. Remember, we're not using the values, we're not using the 0 values. X is less than or equal to rows, and then x plus plus. We're going to say for int y is equal to 1, y is less than or equal to the columns, okay, and y plus plus, like that. All right, and then for each one, we're just going to say cin array at x and y. All right, so this is entering the data. Okay. So the next thing what we're going to do is we're going to set up our pathways. So set up pathways. Right, so in order to set up the pathways, we're going to need an array for that. So we're going to say int pathways is an array of size. Right, so because I already calculated this up here, I don't have to actually do it again. Right, and now this pathways array is going to have to be, originally it will be all zeros, but it's possible for a pathway to have a zero in it. So we are going to actually make a for loop for int x is equal to 0. X is less than size, x plus plus, and we are just going to say pathways at x is equal to -1. And so what that does is it actually populates this whole array with -1s. And then when we are using our current exploration, as we're exploring different pathways, if we ever get to a -1, it means that we've checked every pathway possible and we just didn't find anything. All right. Now, the reason why the pathways array is set where it is to be the size, the rows times column, is because theoretically you could have to visit every single pathway, right? And so, but if you have to do more than that, then it's not possible, right? So, yeah, so you have to potentially have it look and be big enough to store every pathway. Okay. So what we're going to do is we're going to start off by saying we're going to define some variables here. Okay, so we're going to say int empty spot. Now empty spot is just the next empty spot in our pathways array. All right, we're going to say what the current exploration is. So those are both going to start off as 0. So the first empty spot is going to be obviously 0. The current exploration, so the first pathway we're looking at, is also in index 0. Okay, the target that we are looking for is equal to the size. Okay, and what I mean by that is here, because this is the size of this grid is 3, 4, and this is the destination, we are actually looking for 3 times 4, which is a 12. So we are actually looking for this number, and that's going to be our target. Right, so you can see already I've tried to save some operations by not having to calculate row size over and over again. All right, so okay, and then that should be it. Okay, for now. We'll have to add something a little bit later. All right, so we've set up our pathways. Our pathways are all -1. Okay, so the first pathways, so the pathways at empty spot is going to be equal to the array at 1, 1. Okay, so that's the very first top left node that we're going to be looking at. Okay, and then because we populated that, then empty spot is going to have a plus plus to move up to the next empty spot. Okay, what we can do right away is to potentially save time. We can say if pathways at the current exploration, so meaning the current node that we are looking at, is equal to our target. Okay, in fact, we can just say size, so we don't actually need that. So if pathways at current exploration is equal to the size, well, that means that we actually found what we're looking for. So we can actually just say cout yes and return 0. Right, so done. All right, so okay, but what if it's not? Okay, well then what we got to do is we have to, if it's not, then what we have to do is go and look for other nodes that you could go to and add them to our pathways. So in order to look for other nodes, we're going to have to use a nested for loop, right? And it just so happens that this is the for loop that we are looking for. All right, so we are going to say, I'm just going to have to open up the scopes here because we're going to have to put some code in there. All right, so what we're going to do is we're going to say, look, if, so I'm going to start searching the grid, and I'm going to say if x times y, so meaning this is the xy coordinate, is equal to the pathways at the current exploration. Right, so let's go to our diagram. So I'm going to cycle through all these xy values, and I'm going to say, look, if x times y is equal to 3, so 1, 1, no, 1, 2, no, 1, 3, yes, so 1 times 3 is 3, then what do we do? Well, we're going to add that to the pathways. Okay, so we are going to say if, okay, so we're going to say, normally what we would do is we would just say, okay, pathways at the empty spot, okay, is equal to array at x, y, like that. Okay, and then we'd say empty spot plus plus. But hold up, we can't add an item into the pathway if it already exists in the pathway list, right? Because that will allow us to fall into a loop. So we actually have to check the list to see if that pathway, if that potential node is already in the pathway list. Okay, so in order to do that, I'm going to write a method here. So I'm going to say bool already in list, and I want to check the list. In order to do that, I'll need the size, and I will also need the number that I'm looking for. Right, so we're just going to say for int x is equal to 0, x is less than size, x plus plus, and just a simple if statement. So if the list at x is equal to the number that I'm looking for, then return true. That means that the number is in the list. If we get through that without ever returning true, then we can just return false. Okay, so we're going to go and check to see if it's in there. So we're going to say if already in list pathways, so check our pathways, size, and the array at x, y. Okay, and if it's equal to false, so meaning it's not already in our pathway list, then we will add it. Okay, but hold up. Why are we doing this if, what if this node is actually the solution? Then if it's actually the solution, then we could actually just report that it's a solution and we don't actually have to add it, which will save time in our processing. So we're just going to say, before we add it, if array at x, y, okay, is equal to the target that we are looking for, or sorry, it was target, but equal to the size. If it happens to be equal to the size, then we can actually just say cout yes and return 0. Okay, and that's it. Now what this will do though is this will look, okay, so we're looking at this current exploration, so for a 3. Okay, and then what it does is it says, okay, well, is this the solution? No. So what we're going to do now is go and look through this grid and look for cells that can have a product of 3. So no, no, yes. And if it does, what we do is we check if it's the solution. So is this the size? Is this 12? No, it's not 12. So what we do is we add this, we added it to here into the 8, into this position. Then we keep going and we find this 6. 6 is not the solution, so we don't report that we found a solution. But we do add it to the pathways list. Now, this only works now for just the first item in the pathways list. But what we need to do is actually move this up now and do it again for the 8. Okay, so say, okay, well, given that the 8 was not the solution, we are going to go look for other cells that could be 8, right? And so we're going to say that would be potentially 1, 8, which doesn't work, 1, 8, 1, which doesn't work, 2, 4, right? And then we're going to have 2, 4, and we're going to find that 12, which is the target, and that will be the solution. So in order to do that, though, what we need to do is we have to tell the computer to keep repeating this for all the numbers in the pathway list. Okay, so we want to repeat all of this, okay, for all the numbers in the pathway list. So we're going to have to say current exploration plus plus. So we're going to have to move the current exploration up 1. And then we're going to actually say while the pathways at the current exploration does not equal to -1. So as you recall from earlier, we had set all the pathways to be -1. And so as we're adding pathways in, right, they're going to get over, those -1s will get overwritten. But if we do ever get to a -1, it means that we've explored all the possible pathways and we did not find a solution, right? So if we get out of here and we never actually find a solution, that means there's no solution, right? So we can just say cout no, and that's the end of the code. All right, I think we are ready for testing. So let's go take a look and see if it works. Okay, so let's go ahead and run this and put a capital Y instead of a lowercase y. Okay, so the sample data that it gives us in the problem is to say 3 by 4, and the grid is 3, 10, 8, 14, 1, 11, 12, 12, 6, 2, 3, 9. Okay, and yes, it is possible. Great. Now we know that this actually works for all of the, like, for at least the sample that we were given. So what we should do next is throw it into the online grader and see what happens. Okay, so you can see I've added this to the online grader, and we will just refresh. Okay, and so far so good. Correct, and it's actually happening fairly quickly, which is nice. We'll refresh. So far everything looks good, but we are going to actually have a problem. Okay, so like for these first couple, everything is going to be fine. And eventually we will come across a stumbling point. And the stumbling point is that we're going to time out. Okay, so you can see the code is working just fine, and it's going through all these test cases, so I'm confident that my code is actually working correctly. Okay, so we refresh, but you can see now, there you go. On subtask 6, it said, right, and you can see like starting here, it's like 0.8 seconds, 3 seconds. So this one actually took too long, and then probably the rest of them we're gonna skip the test, because if this one is too long, then the other ones will be too long as well. So now we actually have the solution, and if you're happy with that solution, then fine. And you know what, like getting like 15 or 13 out of 15 points on this is acceptable. But I'm going to go through now how to find those efficiencies. Okay, so one of the problems is that checking if this item is already in the list is actually really inefficient, because this is essentially a sequential search. And if your list is 1,000 by 1,000, or if the grid is 1,000 by 1,000, that means the list is 1,000,000 items. And so eventually it's going to take you forever to search this over and over again. And that's one of the biggest problems with this, right, is checking if a number is already in the list. So what we can do is take this out. Okay, so you cannot use a sequential search to look for it. You also don't want to use a binary search. There's actually an easier way to do this. I think it's a kind of a neat way to do it. Okay, so what we are going to do is we are going to create another array. Okay, so we are going to say, let's put it over here. Let's just put it up here. Boolean. So we're going to make a Boolean array called number in list. Okay, and we are going to say that the potential numbers in the list actually is up to 1,000,001. Okay, it's actually 1,000,000 items potentially in the list. I gotta make sure I actually have this set up correct with enough zeros. Yeah, that's correct. Okay, so we have the numbers from 0 to 1,000,000 here. All right, and then what we're going to do, because it's a Boolean array, we are going to originally set them all. Well, they should all be set to be false to start. Right. So what we can do is, once a number is in the array, right, once we put a number in, we can set it to be true in this array, and then we can see if the number is in the array, in our pathways array already, just by looking at the corresponding index in this array. And so we won't have to do any searching. We can just jump directly to it and see if it's there. All right. So when we add a number here, right, so if already in list, okay, so we want to just say So instead of saying if already in list, we are going to say if number in list array x, y is equal to false. So meaning if it's not in there, then we are going to add it to the list. So we're going to say if the number in the list at this index, array x, y, is false, meaning that that number is not there, then we're going to add it to the grid, but then what we will, or add it to our pathways, but then we have to say number in list at array x, x, y is equal to true. All right, so that will actually clean things up quite a bit. It'll actually save us quite a bit of time. Now, if you notice, there are a few other efficiencies that we could find here. One is that we're always having to look up array x, y, right? And so the problem with that is the computer has to do like basically a lookup in the memory to find out what that value is every single time. So what I'm going to do is I'm going to create a variable, just put it over here, array x, y, and all that it's going to be is it's just going to be the array at x, y. And so the first time we use it, we will just throw this up here. So if we do need it, we are going to say array xy is equal to array at xy, like that. And this way we won't have to calculate or find array xy over and over again, and that should save us a little bit of time as well. Right, and so here we can just put that there, we can put that there, and put that there. And so you can see we don't actually have to do like all these like lookups over and over again. Right, so that should help us to save a little bit of time. So let's actually compile this, throw it back into the grader, and see if we have any improvement in the time. So here I've already loaded this up. It's compiling, and hopefully it looks good. Okay, so everything is correct so far. And we had all these like 0.1s here. Down here in subtask 5, I think we had a 0.8. And hopefully we'll see that pick up. I'm glad there's no errors, meaning we didn't mess up our code. Okay, so everything is correct. Now, I believe it was 27 was a 0.8. Okay, so, okay, you can see, oh, there it is. It's probably this one, 26 was 0.8. Now it's 0.5. So it's actually picked up a lot of speed. And then still, you can see we've picked up some speed here, but we actually still are over our limit. So we have to go find still more efficiencies, right? And we're quite a bit over. We only have a 2-second time limit. This went to 3. So we got to actually find quite a few more efficiencies. Now, there are some things that we can do. One of the things that we can do is we can actually change our cin. Cin, because it works on top of this, C++ runs on top of C basically. And so cin has to sync with the standard IO of C. And so what we can do is that takes a little bit of time, so we can say iOS base sync with, okay, and we can actually set that to be false. So we can turn the syncing off, right, which actually should make cin work a little bit faster. That's going to save us a little bit of time, but it's probably not a ton of time. A huge time saver that we can actually do is actually right here. Okay, so we have this do while, right, and we're looking in this row at x. But what we can do is we can actually say, hey, you know what? If this row at x is not divisible by 0, right, that means that none of the y's are actually going to be able to match up, right? So for instance, if our current exploration is an 8 and the x is a 3, right? So if we're in row 3, there's not going to be any value of y that's going to match up. So what we can do is we can just say, hey, you know what? If that's the case, we're just going to skip that row, right? So the way we do that is we're going to just put this in an if statement here. So we're going to say if pathways at current exploration is and modulus x. So when we divide it by the current x value, right? If it does not, if it does equal to 0, right, meaning it is evenly divisible, then yeah, we should search that. We should search all the y's in that row. But if it's not, then we should just skip this, right? So we should be able to do that. And let's go and see if we can actually save any more time by skipping rows that don't work. All right, so here you can see I've resubmitted with the new with the sync turned off, and also with the current exploration checking the row and skipping rows that aren't evenly divisible. Okay, so let's go. Okay, good that we didn't mess everything up. Okay, we have all these compilations are actually going correctly. All right, now I actually did all this and it still wasn't able to beat the time. There's still actually more efficiencies we have to find, right? But I just want to see if it does. If it does, then great. If not, then I don't think it will, but okay. And you can see here, remember we had a 0.8 or 0.3 or whatever, or went to 0.5 or something. Now it's all 0.1. So things are actually happening quite a bit faster, right? And you can see we got down here and everything is fine, but here this one case actually is just too much time, right? But other than that, all of them, and then this one says wrong answer. I don't know how that could be, but okay, but let's we'll worry about that afterwards. Okay, so let's just go and try and find more efficiencies. So when I was actually solving this problem, I was looking at, I just decided to skip the x values, the rows that could not even be evenly divided. And then I thought, you know what, why do we have to look at the whole row of y's? As we're exploring the y's, why do you have to look at the whole row, right? Because, for instance, let's say it's 8 long, and the number we're looking for is 6 or something like that. Right. Well, if x is 2, then we only have to go up to y3, right? Then the other 5 items in the row can be skipped. And so what I did is I actually put in an algorithm that would just check all the time to see if we had gone past the pathways at current exploration divided by x, and then just break at that point if we couldn't do anything there, right? If we've gone past any possible y that could actually be divisible. But I found that because it was checking every single time, it actually created a problem and actually increased the time. So what I decided to do is I said, you know what, I actually just need to pick up a little bit of time. I don't need to do a lot of it. So I'm just going to check periodically. So what I did is I just said if, okay, so y plus 1, all right, so that's the next y that we are going to be exploring, is greater than the pathways at current exploration divided by x. So if the pathways at current exploration divided by x is, let's say, 4, and we're going to go to 5, that means that it's not possible. Everything after this is not possible. So what we can do is we can actually just break this loop, right? And that should actually save us, a lot of searching for pathways that actually couldn't actually work. Okay, so let's put it back in the grader and see how it does. All right, so let's see how we do. I've loaded this up and let's just refresh this. So everything's looking pretty good. So we're going to get down here. See, before these were actually quite higher. Now we're doing it in 0.1 seconds, which is quite nice. Okay, 0.5, still pending judgment. That's not good. Oh, time limit exceeded. Okay, but before this was said incorrect. So when you take a look at it, now it seemed to have corrected itself. But we still have one time limit exceeded, so we still got to go and fix that. So I was looking for more efficiencies, and there's actually a kind of a weird thing in C++, is that this size variable isn't really very quick to work with, and I think it's because I actually don't know the reason why, but I suspect it's because it's probably some sort of keyword, or because it's highlighted the same way C in and C out are, and so it probably has to do with some lookup type thing. So what we can do is change it to be a regular variable. Okay, so something like target, and everywhere where we see row times column or size, we just change it to target, right? Because and that should be it. Okay, I don't see any more instances of size here. So that one actually took me a while to figure out, but it does save quite a bit of time. Anyway, so let's take a look and see if we can save some more time on this. So I'm back in the grader. I've loaded it up and we'll just submit it. While we're waiting, you can see that I have actually changed everything to target instead of time, or instead of size. Hopefully this will work a lot faster. So you can see before, like, these were always 0.1s, but we did have ones that were like 0.3 and 0.5, and you can tell all of them have actually gotten quite a bit faster, right? So as we go, we're going to go down. Okay. See if there's any. Hopefully, the problem with doing this with the grader is it just takes forever sometimes for the grader to get down to these lower subtasks. It would be nice if it could actually just grade the lower ones first, right? Or you could just select it to have a certain section. Okay, so test 34 is our killer. There you go. Right, so test 34 1.9. There you go, 100% on CCC Junior 5. So that's it for the University of Waterloo Junior CCC 5, right? That's actually quite a difficult problem, especially considering it's only S2. But anyways, if you have any comments, put them into the comment section. Remember to like and subscribe to the channel. Thanks for watching, and I'll see you next time.